Okay. Good afternoon, everyone, and it's good morning still in Iran. And welcome back again to the workshop on numerical astrophysics. So in the last two lectures or the modules, we basically first looked into how to derive the standard MHD or ideal MHD equations, and then we went into some details of how certain codes, or there are various codes, but how certain codes actually tackle some of these important aspects, basically solving a conservative equations. And now in this module, this module and the next one, what I will do is basically I will describe how PLUTO Code actually works out, and then basically provide some idea of how to basically get started with PLUTO Code. So this is a code that has been developed in Torino, and the main developer is Andrea Mignone. And basically I'm part of the development team, and we have been working, I've been working since like now 10 years or so on this code. So now let us basically give some sort of an idea of how this PLUTO Code is, how to start and get used to it. So this will be a short lecture, about 30 to 40 minutes, and then we'll take a break another, and then we'll start basically with some exercises, and then some exercises. So that would be the case, and in the next session it's all open for questions, and all sorts of questions that you have with regard to code, with regards to the earlier modules, please go ahead and ask. So the next session after this one would be more informal, where you are more open to ask questions, and I will demonstrate certain aspects here. Okay, right. So let us start with PLUTO Code essentials. So here the basic idea we talk about is installation, setting up a problem in PLUTO, compiling and running the code, and visualization of the data. And then finally some features of the PLUTO Code and some examples that we will look into it in the next session. So there were some questions. Of course, the PLUTO Code requires basic C compiler. If you're using serial, it's GCC. If you use parallel, it's MPeach library, which is version 2.0 or plus, or you can use 3.0. Now it's a compatible. And there are other MPI compilers like MPI CC, MPI Run, MPI Execute, etc. and so on. For Python right now, so Python version 2.7 plus, and now it has been, now the version that you have, it's also Python version 3.6 plus, so you can use now Python 3, because Python 2 now is not anymore updated. So we have translated everything to Python 3, and the version that I've sent, and it's on GitHub, is basically also compatible to Python 3.6 plus. It basically also has AMR options, but AMR you require C++ compilers and an additional library called the Chombo library and HDF5 file format. So this is only for AMR. We will not go into AMR, at least in this workshop. For data analysis, as I said, you can use Python 2.7 or 3.5 plus, GNU-plot, Ideal, or sometimes if you are interested in doing 3D rendering, I would suggest LLNL Visit software. It's up to you to download, or Qtware is also ParaView software, which is available completely open source. So these are the visualization and data analysis software. So the code has a web page. It's called plutocode.ph.unitor.it, hosted at University of Torino. And basically, when you download or install a code, it comes in a tar.gz file. The idea is basically just untar the tar.gz file, and you should be fine. And you basically, the idea is that first you have to define a Pluto _dir in your shell using this export functions like export Pluto dir part to the Pluto directory, or if you're using a shell script, then it is this thing. So it's a bash script, it is this thing, and otherwise shell script is this thing. So this is the way you basically install the code. So I think the code version that I've given is already there in the GitHub. It's a tar.gz file. You can just install it right away and you can use it. So as far as the documentation is concerned, there is an extremely comprehensive documentation available, and the latest version that we have is June 2018, the version 4.3. Though there is a version which will coming up soon, maybe in a month or two, which is version 4.4, and that will be made public in a couple of months. But right now the public version is version 4.3, and there is basically complete documentation available on the web page, and that one can refer to. Here I will basically target certain aspects which are essentially to set up a simple Pluto problem. So I'm assuming that some of you have used Pluto, some of you may have not used Pluto. So I will basically start from scratch, assuming that not so many people have used Pluto or have not used Pluto right now. But basically I will start everything from scratch, and if people have used Pluto, it will be useful for them to understand what is going on. So the question is that whenever you want to describe a problem, so let us say you want to solve a problem, you basically have to define the problem first. And that is one of the important aspects first to define a problem. So the question that you should ask while defining a problem is that what is the underlying physics? For example, if I want to study, let's say, a solar wind interacting with magnetosphere, whether the problem has magnetic fields, yes or no? Yes. Is the flow relativistic? No. Well, you can treat it with non-relativistic and then go on. That's not a problem. Now the question that you need to ask is what geometry you wish to solve the equation. So for example, if I want to solve a magnetosphere, the Earth's magnetosphere, you will prefer a more sort of a spherical geometry, but you can also do it in Cartesian geometry. Then you might want to ask whether my problem can be solved in just 2 dimensions or it really requires the 3 dimensions to accurately capture the physics. Then the question you will ask is whether my system requires additional non-ideal terms. Let's say, for example, if I do an accretion disk problem, yes, viscosity is important. So then your problem requires additional non-ideal terms, and therefore you need to add source terms. And then you should see which of the conservation equations are affected. So for example, if you add viscosity, your momentum conservation and energy conservation are affected. Or similarly, if you want to take magnetic resistivity, then your induction equation, the energy equation are affected, and so on and so forth. So then what are the physical conditions at the boundaries? For example, if I want to basically have a system which is periodic in nature, then I do not worry about the boundary conditions and I put periodic boundary conditions and it will work. And then if you want to have a solution in which your material comes from the jet, or materials comes from in a jet, then you will need to import some boundary conditions in the jet, and that basically makes your boundary condition dependent problem. So the question is what time scale you want to simulation up to. So these are the different questions first, and based on these questions you can actually define problem. So as I said, I mean to say, in a solar wind Earth's magnetosphere, what are the underlying physics? Non-relativistic with magnetic fields. In what geometry do you wish to solve the problem? 3D, ideally spherical, but okay, you can do Cartesian. You can have the grid which is 20 times the radius of the Earth, 20 times radius of the Earth, and in Z direction 100 times the radius of the Earth. And the Earth is centered at 0,0. That's a problem. Yes, in this case, gravity is there to support Earth's magnetosphere or the atmosphere. What physical conditions would be used to prescribe boundary conditions? So in this case, you might want to have a solar wind coming and hitting the Earth. So at one of the boundary, you should have solar wind on the left Z axis and free flow of all possible direction. And what is the time scale? So for example, if I want to study the steady state behavior of a magnetosphere, I just evolve it till the steady state time scale is reached. So that means not much more motion is happening in your system. So that is essentially how you define a problem. So in order to start, the idea is that you basically have an interface. So you basically go to your directory wherever you want to set up a problem. So you can define a separate problem. So it's Pluto dev, in this case it's Pluto dash 4.3, and Pluto dir is there, but this is a working directory. And then you can just go to a simple problem, and you can, it's just a blank folder, and just run this Python script, which is Pluto dir setup.py with options. And you can actually get this screen, which is giving you a setup problem, change, make file, auto update, save, setup, quit. So you click on the setup problem. Oh yeah, by the way, you can actually have more options here. So for example, if you do not put any options, it goes by default, but you can have options here that with finite difference. So for example, if you want to use finite difference scheme, which is already implemented in Pluto, or you want to use something like a shearing box, mostly important in accretion disk problems. Also Fargo or Chombo, for example, if you want to use AMR, or we have now newly introduced particles, and therefore you can also do with particles. So these are the different options that are available with Pluto, but by default option, it basically solves the standard ideal MHD or ideal HT equations without any source terms. So now the first thing is, let us do, so for example, if I suggest you to go into your SR test problems and look into magnetized non-relativistic blast wave. So I'm just quickly going through it, and you can actually work out at a later stage while we are having question answer sessions, and you can work out this thing, and I'll help you work out these kind of things together so that it's easier for all of us. But I just would like to briefly go over each of these files so that it's clear to you. So the first is what you want to target is a definitions file. So there in the Pluto version that I've sent, if you go into test problems in MHD, there's a blast wave, and you can look at any of the definitions file that is existing. You can see physics, which is MHD because it's a MHD magnetized blast wave, non-relativistic, that's why it's only MHD, not RMHD. And it's done in 2 dimension and 2 components. 2 dimension and components are essentially dimensions means X and Y. Sometimes you may have do work in 2 dimensions, and you can assume the 3rd dimension to be cyclic or periodic in nature, and then you can do 3 components also. The geometry is Cartesian, so it's X and Y. There are body force is gravity. There's no gravity. Force turbulence is just reconstruction. This is linear. This is reconstruction is how you interpolate the cell-centered quantities on the interface. So this is a linear interpolation. So essentially that's there. Time stemming is RK2. As we discussed, how do you update the conservative from UN to UN plus 1? And that is a Runge-Kutta 2. This I think something you must have studied in your n-body problem also, a Runge-Kutta 2 method. Dimension splitting is essentially you treat all these 3 dimensions equally. Do not treat it differently. And tracer is essentially another tracer kind of which basically evolves an advection equation. And then there are 7 user-defined parameters. So we'll have a look at it. Then you have a physics-dependent thing. You have defined your equation of state. Here you can see the divisions of B control. This is basically where you can define your method or divisions of B control. It's constant transport or divergence cleaning or 8 waves or none. So you can define it here. So this is the place where you define. And these are the different user-defined variables that you have. So you can define resistivity, Hall MHD, thermal conduction, viscosity if you want to. Otherwise it's no. Then you can have P in, P out, magnetic fields, theta. These are the input parameters that you can give. So this is slightly more complicated, and for expert users, these are essentially the limiters that you have, slope limiters. These are averaging procedure which are used to average out the electric fields that you compute at the phase edges and so on and so forth. So these are slightly more expert user based, but right now this is there. The second file that you want to modify is basically the Pluto.ini file, which is actually giving you grid information and some timing information. And definitely the most important is the solver here. So this solver is rho, which I have not discussed, but you can put here HLL or HLLD or TVDLF. There are various solvers that are existing, but essentially you can put whatever solver you want to put over here for your problem. Okay, so that is essentially the case, and this is t-stop is the time where you want to stop your simulations. So that is basically your t-stopping time. Then you have all your boundary conditions to be given here. X1 beg is at the beginning of the, so if it's a Cartesian, it's X beg, and X1 end is X end, X2 beg is Y beg, and X2 end is Y end, and so on and so forth. And in this problem, all of them is an outflow. That means all the material will basically just leave the domain. So that's basically the, you can put your reflective boundary conditions or periodic boundary conditions, or you can also define a user-defined boundary conditions where you want to, let's say, put some material coming from outside to inside and so on and so forth. So all these things are available with Pluto. Then comes an important part which is useful in analysis, basically how much you want to save your data. So for example, if you want to save your data every time step, so this is how you do it. So for example, in this case, how frequent you want to save the data and how frequent you want to write the log file is basically can be controlled from this static grid output. This is basically the same thing but for AMR. And then there are these different parameters are there. Essentially the parameters are what you give as input conditions, and this is essentially you give as the parameters block. So you can give all these input parameters which goes in the init.c file. Okay, so these are the things. And now this input parameters comes basically in your init.c file, which is a C function, init function, which is where you basically give the heart to the code, what you want in the code. So for example, if I can go quickly through this, essentially you define some 1D vectors. So these are called V and vars. So this is an array, or in this case it's US, this doesn't matter. It's an array of primitive variables. So you give what are the initial value of densities, let's say 1 in this case, velocity is all 0, and the pressure is the outside pressure that you give. So for example, in the blast wave, what I have is basically spherical blast, a spherical region with very high pressure and high density, and outside it is low pressure and low density. So this is and static. But then if my radius is less than this, then my pressure is nothing but an inside pressure, which is much higher, because if you look, see my inside pressure is 10 to the power 3, whereas my outside pressure is just 0.1. So 4 orders of magnitude difference between the pressure, and that you can put it here. And then you can define some theta and magnetic fields and so on and so forth, and then you can define your this thing. Well, if you are interested, you can also define the vector potential instead of the magnetic fields. I said assign vector potential to yes. So in this case, what will happen is that if your geometry is Cartesian, it will neglect this part. It will not read this, but it will only read the vector potential part, and it will compute the magnetic fields accordingly. The advantage of this is that when you use vector potential and constraint transport, you have extremely good accuracy in divergence of D control. So that is very, very important with regards to the way you initialize this. So this is where your initial conditions are initialized. And then what you do is you choose your makefile. So the next thing is you basically go into makefile, and you can choose any of the makefiles. There are certain existing makefiles. Depending on the configuration that you have on your desktop and laptop, you can choose a makefile. And that is essentially Darwin, GCC, MPICC, or Linux or whatever. And then finally, if you make after choosing this makefile, you can make it, and then you basically get an executable Pluto. So you basically get a Pluto executable which you can actually run your code in. So one of the good practices that you can do a command if you're using Linux is LDD Pluto. This will help you to find out all the libraries that are linked to the Pluto, and you can see that if all the libraries are linked, and that will help us to basically start running the Pluto. So for example, if you're running just Pluto with a single processor, then you just say /Pluto and it runs. If you're running with 4 processors, then you use mp execute -n4 /Pluto. But here in this case, you have to ensure that the makefile is mpicc.deps, because that's a parallel compiler. And at the end of the run, you will essentially have .log files and .out files separately, where grid.out will have information with regards to grid, and that is important for visualization. And .out files will have all the information with regards to the timing for what variables are stored at different times. So this is basically a typical output looks like, a log file looks like. You have some instruction, and then you have some definitions of what you have defined as scale density, scale pressure, scale velocity. Here you see this is a run with a single processor. The processor size is 200 times 200 grid cell. And you have started the computation, it runs, and it saves another file. And this gives you like the summary that how much time it took and so on and so forth, and when did it run and so on and so forth. This is an old run which I've just taken a screenshot. And for parallel job, it will write its own log file for each processor. Okay, so and the frequency you can choose from there. So there are other options which are also available. So when you run Pluto, you can always run it with restart option. So for example, if you run a simulation and then it stops, and then let's say your computation time stops, and then you want to again run it again from the last time, then you can just say -restart n. Say for example, you want to run your simulations for at least 100 steps, then you can just say -max steps 100. This is useful for testing. Suppose you want to run your simulations but don't write any data files. Sometimes it's useful to check how faster the simulation is running, and you can just write no write. And you can also basically vary the resolution by changing n of x. like with XRES function. So these are basically the different options that are available, and you can find all the information in the data. There are different data formats that PLUTO Code supports, with single file format and multiple file format. So the most default is the .dbl file format, which is actually the native binary in the double format, so double precision. And you can save it as a single file, which means that all the variables are stored in a single file, and it's data.000.dbl or data.001.dbl. Or you can save it as multiple file format, means that each variable is stored separately. So you'll have row.000.dbl, row.001.dbl, and so on and so forth. Same thing with the FLT format, but it is just a single precision format. Then you can use something called as a VTK, which is Visualization Toolkit format, which is useful for visit visualization. Same with HDF5. And then there are other formats which are very old. It is TAB and PPM, which usually do not use it for general runs. There are all these 4 file formats that you can use effectively very well. As far as the visualization is concerned, there are several softwares that are provided, several visualization tools which though this is a GUI version that I put, right now we only have the command line version, which is the GUI version was old and basically used only for testing purposes. But we have a very sophisticated command line version which you can download now. With the tarball that I've sent to you, or it's in the GitHub, the live Pluto version has been updated to Python version 3.0. So you can actually download that, and you can untar that, and you can use it very effectively, absolutely no problem. And you can start using it. So once we in the next session, when we do hands-on, I will show you how basically we can do all sorts of visualization, so that we can do it together while we are doing it, and then we can have open for questions. So this is PyPluto is one visualization software. However, it doesn't support 3D visualization. It's only for 2D and visualization from 2D and 1D perspective. You can use, as I said, Visit, which actually has a very useful tool, and it supports a VTK and HDF data file formats, and extremely useful for 3D visualization. And it's available online, open software is available, which you can download easily. There are various physics modules, as we discussed. There is hydrodynamics, magnetohydrodynamics, special and relativistic hydrodynamics, special relativistic magnetohydrodynamics. We do not have general relativity as of yet, at least in Pluto, but we don't know about future. However, what we have done recently is we have incorporated particles, which are essentially Lagrangian particle-based modules, and they are useful in various aspects of simulations. And then there are MHD pick and dust. I will not go in details of this. As far as the divergence B constraint is concerned, we have Powell 8-wave method, divergence cleaning approach, and constraint transport. These are the things that I have described during my last lecture as well. So these are all the things available in Pluto effectively. As far as the non-ideal physics, which I could not cover in my lectures, there are various things which are available, which is gravity, both in vector and potential format. You have optical thin radiation cooling, you have force turbulence, ambipolar diffusion, Hall effect, resistivity, thermal conduction, viscosity, and you can have an option even for working in rotating frame. For example, if you want to study the, let's say, hot spots on stars, then you can go in the rotating frame and you can basically add Coriolis force into your momentum equations. And then there are also options for various equation of states. So for example, if you want to study some very exotic object with different equation of state, you can also do that with Pluto. So all these things are available and can be utilized. Of course, as I said, I'm not going into details of the adaptive mesh refinements, but Pluto do have adaptive mesh refinement incorporated, and essentially the idea is that it basically selectively resolves certain regions and make it much more resolved. And this is one such image from a magnetic rotor problem where I've overdrawn these regions of very, very high gridding structure, especially resolving high density structures. So this is AMR. I'm not going into details of how AMR is done. And this is basically using Chombo library. So now in the next part, basically I'll just stop here, or at least because it's slightly early. So what we do in the next part is I would request now, since we have some time, what I will request all of you is that you can actually install all your Pluto version, so that in the next thing I will discuss about the HT sawtooth problem. We will do it together. We can maybe see what we can do together, and then an MHD blast wave problem. And then I will leave some problems for you to solve, so that you can actually take it up on your own, completely at your own this thing, and you can basically, I will try to guide you on how to do it, but it's completely your choice on how to do it. So so the first two problems I will take it up in the next session, and I would also open it for all questions that you have. So maybe we can also start the questions now, and then we can have more questions at a later stage. So I'll stop here for this thing. I knew that this was a smaller thing, but in the next session I will I'm really doing the coding together. So I will stop here, and I will take questions. So it's just a 30-minute thing, but I will take questions if you have now, or we can basically come after 15 minutes and start with the coding of Pluto code, and then I will keep it open for questions. Completely up to you.
Thank you very much, Bhargav, and thanks for your great talk. Now we will have well, some questions. Hamid here wants to ask a question. Hamid, could you please go on and turn on your microphone and ask your question? Thank you. Apparently, there is no question. Anybody else here has a question? Mohammed, please go on and ask your question. Please turn on your microphone.
Yeah, just to know, does Pluto support periodic gravitation?
Sorry, self-gravity?
No, periodic boundary gravitation.
I didn't, the gravitation in the sense?
Yeah. For
No,
example,
it has a body force routine, which basically handles gravity. A point source gravity function can be handled as a source term. Either you can use it as a vector quantity or a scalar quantity, or a potential. You can define a potential, and it will compute the gradient of the potential and therefore the force, which goes into the momentum and the energy equation. Or you can directly give the acceleration due to gravity, due to a point source or something like this, or just like and then it will take care as a source term. As far as self-gravity is concerned, it's not incorporated in the version of Pluto that is available.
Thanks.
Okay, thank you. Hamid here has written his question, and the question is, I am curious about simulation of effect of magnetic field on fluid flow with nanoparticles. How good or effective is Pluto in this? Is it effective at all? Thank you.
Right. Hamid, thank you for your question. See, as I was mentioning earlier, it all depends on the scale. So as you said that you are interested in nanoparticles, fluid flow with nanoparticles. Now, you will have to define the scale that you are interested in. So for example, if nanoparticles, I would say it has 1 nanometer. Each particle basically has a size of 1 nanometer. Now, the question is, if you want to describe the flow of nanoparticles with the same set of equations, if you could describe your flow, whatever problem you are studying, and you can describe with the same set of ideal MHD equations that I have described and derived, then yes, you can use Pluto effectively. But it's all about the scale that you are defining, and that scale is extremely crucial. See, if you take an ideal MHD problem, it's completely scale free. Okay, it doesn't have any scale, so you can do it. The same set of equations can be used to study, let's say, stars. It can also be used to study jets, and so on and so forth. All depends on what physical units you define, and that physical units have to be consistent with your problem that you choose. So if your problem that you have in mind, which is fluid flow with nanoparticles, can be addressed or with the set of equations that I have described or derived, then yes, Pluto is effective to do that. But you have to be careful. Yes, ideal case is scale free, of course, always ideal case is scale free. Yeah, hope this answers your question.
Thank you very much. Asiya, if you have any question, you may. Okay. This is a question by Asiya. She asks, could you please explain a bit about the computer clusters that one needs to run a typical HD, MHD, etc. simulations with Pluto? Thank you.
Thank you, Asiya. This is a nice question. See, Pluto Code, when it was formulated, it was always meant to heavy simulations are sometimes very computationally heavy. So the Pluto Code was designed in a manner so as to scale. If I tell you scale effectively to very, very large number of processes. What it means is that, say for example, a computational task takes 10 hours with one processor. Okay. Ideally, if you use 10 processors, then it should take 1 hour. So that means it's ideal scaling. That means all the tasks are divided equally among these 10 processors, and therefore the time will be reduced by 1/10. Okay, so typically Pluto Code scales extremely good up to 16,000 or about 20,000 processors. That's absolutely no problem with the current thing. But you see, the way computing is going on, the way the computing is evolving, everything is going into GPU and so on and so forth. So if I just restrict myself to only core-based or CPU-based computing, it all depends on the problem definitions that you have. So for example, if I just want to solve a simple blast wave problem, just study the test of a blast wave, then it may even take one processor. But if I want to, let's say, study a complex interaction of neutron stars with a white dwarf and so on and so forth, then it will be a slightly more complicated problem. It will require much more higher computational power, and it can go up to tens or hundreds of processors. So that completely depends on your problem that you choose, and it all depends on the infrastructure that you have. So ideally you can run, ideally I would suggest that if you have a very computationally heavy, you should run it in more number of processors. But if you have a very light problem, don't run it in more number of processors. That's just wastage of processors. I hope this answers your question.
Thank you very much. Well, it seems that we don't have any more questions here. So I think it's good if we have a 15-minute break. Okay, is that okay?
Yeah.
Okay. Thank you very much. Sorry, I didn't hear you. There is a problem in connection.
So we can join at 1:30. It's 1:10. Yeah. Yes.
Okay.
1:30.
So is it okay? 1:30.
Yeah.
Okay, great.
So that will be my last session, where I will basically do some hands-on with Pluto Code. So I would request everyone that in these 20 minutes, maybe you can install whatever tarball has been given to you. And Hussein, I will share all the slides after my talks to you, so that you can basically upload it wherever you require.
Thank you very much. We will certainly upload the slides as soon as we receive them. So we will start again at 12:30 Iran local time and 1:30 India local time. Thank you all. Yes. Stay with us. Have a good time.
Thank you. Yeah. Thank you. Bye-bye.
Goodbye.